Have you ever stood barefoot on gravel? It hurts, doesn't it? But walk on a smooth floor and it feels just fine. The reason behind this simple everyday difference is pressure. Hi everyone! In this lesson, we'll explore the physics behind thrust and pressure, and trust me, these ideas pop up all around us. Let's start with thrust. Thrust is just a force, but one that acts perpendicularly to a surface. It's measured in newtons, just like any other force. Now comes pressure. It tells us how much force is applied over a given area. The formula is P equals F divided by A, where P is pressure in pascals, F is thrust or force in newtons, and A is the area in square meters. So, if you apply the same force over a larger area, the pressure decreases. Simple but powerful. As you'll see in the diagram, the same force pressing on different surfaces causes different pressure effects, and that has big consequences. Let's move deeper. Now imagine two people, both applying the same force, but one uses a sharp knife and the other uses a spoon. Who cuts faster? Of course, the one with the knife. This shows how pressure increases when area decreases. Mathematically again, P equals F divided by A. If F stays the same and A gets smaller, pressure goes up. On the flip side, increase the area and you spread out the force. Pressure goes down. This is why wide tires help tractors move on soft soil. They reduce pressure so the heavy vehicle doesn't sink. In the diagram, notice how the sharp knife applies high pressure over a small area, while a blunt one doesn't cut well at all. Physics in the kitchen. Let's take a walk through daily life where pressure principles are everywhere. Nails and drawing pins have pointed ends. Why? To focus the force on a tiny area and increase pressure, making it easy to pierce surfaces. Camels and tractors, they walk on soft terrain. That's why they have broad feet or tires, spreading their weight and reducing pressure to avoid sinking. Skis are wide for the same reason, to glide over snow without sinking. Building foundations are broad so the structure doesn't press too hard on the ground beneath. It's amazing how engineers, nature, and physics all follow the same rule: less area is equal to more pressure, more area is equal to less pressure. Visuals here really help, from shoes to pins to desert animals. Let's compare how solids and fluids behave when applying pressure. Solids apply pressure only in the direction the force is applied, usually downwards. But liquids and gases, being fluids, behave very differently. They exert pressure equally in all directions at a point. This makes them powerful and a bit tricky. In fact, this is why a dam wall is made thicker at the bottom. The pressure from water increases with depth, not because of container shape, but due to height. And here's something important: Pascal's law applies only to fluids, not solids. It tells us how fluids transmit pressure uniformly when confined. We'll look at that in detail in the next module. Did you know you're being pushed by thousands of kilograms of air right now? That's atmospheric pressure, the weight of the Earth's atmosphere pressing down on us. At sea level, it's 1.013 times 10 to the power 5 pascals, or 1 atmosphere. But don't worry, your body is already pushing back. That's why we don't feel it. There's perfect balance. Here's a cool experiment. If you heat and seal a metal can and let it cool suddenly, it crumples. Why? The pressure inside drops, but atmospheric pressure outside remains, crushing the can. In the diagram, you'll see arrows from all directions showing this uniform pressure in action. Air isn't just what we breathe, it's a physical force. Time for some numbers. Problem: A boy of weight 600 newtons is standing on 1 foot. The area of contact is 0.03 square meters. What's the pressure on the ground? Let's solve this together. We use the formula P equals F divided by a substituting values. P is equal to 600 divided by 0.03. Now calculate 600 divided by 0.03 equals 20,000. So the pressure is 20,000 pascals. That's 20,000 newtons per square meter just from a single foot. And if he stood on both feet, the area would double, so pressure would halve. Always remember, same force, bigger area, lower pressure. Visual here shows how pressure focuses through a smaller contact zone. Let's quickly revise what we've learned today about thrust and pressure. Thrust is the force acting normally to a surface. Pressure is how that force gets spread out over an area. The key formula is P equals F divided by a pressure increases with more force or with less area. That's why knives are sharp and elephants don't sink in mud. Solids press in one direction. Fluids push in all directions. And the air around you? It's pressing on you every second with 1.013 times 10 to the power 5 pascals of pressure. So next time you walk in sand, or push a pin, or even open a soda, you'll know it's physics in action. I hope you now have a clearer understanding of how pressure shapes the world around us. See you in the next session with another fascinating concept of physics.